Here's a problem we didn't get to in class today. It's the second one here, to calculate the pH of a bleach solution at 25 degrees. If you go into the supermarket and buy bleach, it's a 5 weight per volume solution of sodium hypochlorite, NaClO. This compound, sodium hypochlorite, is the conjugate base of hypochlorous acid, HClO. You're asked to calculate in this problem the pH of a solution, and this is the concentration given here. The answer to this problem is very similar to the answer of the problem we did before, except instead of given a weak acid, acetic acid, we're given a weak base. And also, we need the Kb, we're given the pKa. So keeping those things in mind, we're going to jump right in and do the problem. What I'm going to do is abbreviate that base as B. And remember, when we add this to water, what happens is that, and this will be an equilibrium, be a weak base, that the base acts as a Bronsted-Lowry base, abstracting a proton from water to become protonated, BH+, and then that is the conjugate acid of this base. Here's the acid, it's donating a proton to B, and we're forming the conjugate base of H2O, which is OH-. Okay, we'll set up the ice table like we did before. The initial concentration of base given in the problem is, it's not molar. If we're going to use Ka, which is a Kc, we have to express the concentrations in terms of molar. This is a weight per volume. But we know from our earlier study of concentrations in the solutions chapter that we can convert units. So a 5% weight per volume, this implies you have 5 grams of the solute in 100 liter of solution. So let's change this concentration unit into molar. We have to know what the molar mass is. Molar mass of sodium hypochlorite. Well, we can do it a couple ways. One is you just type in molar mass, NaClO, into Google, give you the molar mass, or you can add up the molar masses of the individual atoms here. Either way you do it, you find out that the molar mass is 77.4. So if we have 5 grams, we divide that by the molar mass, 74.44 gram per mole. That's the number of moles, and we're putting that into 0.1 liter. 100 milliliters is 0.1 liter. This is 0.672 molar. So that's our initial concentration that we can put into the ice table. We're not going to worry about water. Water is a pure liquid, does not appear in equilibrium expressions. Initial concentration here is 0. Initial concentration here is 0. And by writing a 0 here, we are ignoring the autoionization of water. As we mentioned in class, we can do that because the amount of OH produced is very small by the autoionization of water. Most of the OH in the solution comes from this base reaction. All right, well, let's see. We have most products there. X will go away here. X will be produced here, and X will be produced here. So the equilibrium concentrations, 0.672 minus X, X, and X. All right, now if we had what Kb was, we can immediately write down the equilibrium expression using X. But if we go back to the problem, we don't know what Kb is. In fact, we're not even given pKb, we're given pKa. But as we discussed in class, we know that the pKw of water is equal to the pKa plus the pKb. And we know at 25 degrees C, that's the temperature at which we're asked to calculate the pH, the pKw is equal to 14 two decimal places or two things after the decimal place means two significant figures when you're talking about logs. So let's do that. So the pKb, which we want, is equal to pKw, 14.00, minus pKa, which is given in the problem 7.50. So the pKb is 6.50. And then the kb will be just that number raised in the exponent here, 10 to the minus 6.5. All right, so now we can finally, with our ICE table, write down the equilibrium expression using these equilibrium concentrations here. So we have 10 to the minus 6.5. That's equal to x squared over, the initial concentration was 0.672 minus x. Let's ignore x for now, and we'll do a check and see if we could have ignored x, if that's a good idea. So now we have 10 to the minus 6.5. That's about equal to, we're ignoring x squared over 0.672. Let's solve this equation for x. X will be equal to the 10 to the minus 6.50 times that initial concentration, 0.672, raised to the 1/2. That is 4.61 times 10 to the minus 4th. All right, let's see if that's a small number compared with the number we're subtracting it from. Recall that when we ignored x, we had 0.672 minus x. Is this x small compared to that number? Well, I think it is, but we'll go ahead and go through the exercise. 461 times 10 to the minus 4th over 0.461. This is less than 5%, so we're okay to ignore x. And we don't have to do any further calculations, no iteration or no solving by the quadratic equation. So we now have what x equals to, and sometimes it's good to go and check what x actually is equal to. We look up here, oh look, x is equal to the OH concentration. So we can do a couple things here. Let's first calculate the POH. The POH, P, recall, stands for minus log. So this would be minus a log of the OH concentration, which we said was, this is the OH concentration. So minus log of 4.61 times 10 to the minus 4th. So that's equal to 3.34. And the problem asked us to calculate the pH, so we know that the pKw is equal to the pH plus the POH. Well, that's interesting. Let's take a minute here and contrast and compare. Oh, look, pKw is pKa plus pKb. pKw is pH plus POH. Interesting parallel. So that the pH is, well, we can write down what pKw is. We know at 25 degrees that's 14.00. We subtract off the POH, which is 3.34. So finally we get the pH to be 10.66. And that's it.